In the previous module, we talked about how Huygens' principle can explain the phenomenon of diffraction of light around corners or through openings, even though individual rays of light always travel in straight lines. Huygens' principle also explains how light passing through a small slit can diffract and interfere to create an interference pattern. In the previous module, we just used a single slit, but what happens when we increase the number of slits that allow light to pass through? If we shine light on two slits that are very far away from each other, each slit will produce its own single slit diffraction pattern with a large central bright spot opposite the center of each slit and alternating dark and light fringes on either side. As the two slits get closer, however, the two wavefronts coming through each slit will begin to interfere. This will give an overall pattern similar to the one we saw when we had two point sources. This diagram shows a plane wave striking a barrier that has two slits in it. The wavefront emanating from each of these two slits will interfere. The print on this slide is a little bit hard to see, so I'm going to go ahead and draw over some of the wavefronts, but hopefully if you look very closely you can see the second wavefront interfering with the first. When the light from the two interfering wavefronts hits the screen, you get an alternating minimum and maximum pattern with the maximum in the middle. This bar right here shows the relative intensity, so you can see that the points of low intensity correspond to the minimums and the points of high intensity correspond to the maximum. Here on the right is a screen capture of the PhET simulation with the two point sources which are radiating outwards and causing an interference pattern. So you can see that each point source has these semicircles that overlap and interfere, which are very much like the semicircles from the wavefront coming out of the two slits. But the two slits are not point sources. They are each a line of many point sources, according to Huygens' principle, with their own diffraction and interference patterns that will also affect the overall double slit pattern. So as the two slits move closer together, these individual diffraction patterns will merge. The result of the two distinct single slit patterns overlapping, ignoring for now the interference with each other, looks very similar to just another single slit pattern, as if this pattern was made by one big slit, with a large fringe centered on the screen, directly opposite to the point halfway between the two slits. However, the center fringe is not as bright because it is effectively missing a large chunk of light that would be coming from the center of a large single slit. The net result, including the overlapping of the two distinct single slit interference patterns and the interference between the wavefronts from the two slits, is a sort of overlay of the one slit diffraction pattern for each individual slit, plus the alternating bands of constructive and destructive interference from the two wavefronts. This forms a pattern of alternating light and dark fringes, as you would see with two point sources of light interfering, but with the maximum intensity of each fringe determined by the intensity that would be present at that point if it was just the overlapping single slit diffraction patterns. The dotted orange lines show what this maximum intensity is. The shape of these dotted lines is called the single slit diffraction envelope. The image on the far right shows you what the double slit diffraction pattern actually looks like on a screen. For single slit diffraction, we found the location of the dark fringes by finding just the right angle so that the path length difference between two rays, a distance of the width over 2 apart, was equal to 1/2 the wavelength. Unfortunately, with two slits, the central ray that we measured this angle from is effectively blocked out. However, we also said that as long as the 2 points keep the same spacing, the width over 2, they will have the same path difference. So the path difference between ray P1 and the center ray is the same as the path difference between the center ray and ray P2. This means that the path length difference between ray P1 and ray P2 is just 2 times delta L. This means that we could say that W sine theta equals 2 times delta L, where we are still measuring the angle theta from the center line, whether or not the ray emanating from the center line is blocked. If instead of the width of a single slit, we use D, the distance between 2 points at the center of each of 2 slits, this relationship is still true, giving us d sine theta equals the path difference between a ray emanating from each of these 2 points. As before, we compare rays that are separated by the same distance d, starting with the pair at the top of each slit and moving down to the pair of rays at the bottom of each slit. So again, all that remains is to find the particular angle that will give us the desired path length difference. That is, a multiple of lambda for totally constructive interference, or a half integer multiple of lambda for a path length difference that gives totally destructive interference. I want to take a moment to show you how I got that formula for the destructive interference, which requires a half integer multiple of lambda. So we can say that d sine theta equals either lambda over 2, 3 lambda over 2, 5 lambda over 2, etc. If we go ahead and pull the lambda out of that, since that's what they all have in common, then we have d sine theta equals 1 half, 3 halves, 5 halves, etc. times lambda. This can just be written then as d sine theta equals 1 minus a half, or 2 minus a half, or 3 minus a half, and so on and so forth, times lambda. So that number, the 1, the 2, or the 3, is where I'm getting m in the formula. And that leaves us with d sine theta equals m minus a half times theta. Notice that if m equals 0, you just get d sine theta equals negative 1 half lambda. This is still a half integer phase shift, so it will still result in totally destructive interference, and it will still give you a dark fringe. So in this case, we can still use m equals 0, and it won't change our answer. Okay, so what if we keep going to 3 slits? The bright fringes are much narrower, and you can now start to see a pattern even within the bright fringes, where you have some bright fringes that are very intense, represented by the longer or taller peaks on the plot, and some bright fringes which are not very intense. The brightest fringes, whose intensity is limited by the shape of the single-slit diffraction envelope, are called principal maxima. But really not a whole lot changes. You still get these big, intense, bright spots, the principal maxima, and you still get a single-slit diffraction envelope. The biggest difference between double slit and triple slit is that the principal maxima are much narrower, and they're also much brighter in intensity. With 5 slits, the principal maxima get even narrower and even brighter. We could continue adding more slits indefinitely. The equation for the location of the bright fringes for any number of splits is still the same as for double slit diffractions. D sine theta equals m lambda for constructive interference, where d is the spacing between each slit. The equation for destructive interference also remains the same. Recall that longer wavelengths with respect to the width of the slit bend more. So red monochromatic light with a wavelength of around 700 nanometers will diffract at a slightly larger angle than blue monochromatic light with a wavelength of around 450 nanometers. Since the peaks on a multi-slit diffraction pattern are so narrow, this slight difference in angle will result in 2 different sets of peaks. That is, if you shone a laser made of just those 2 wavelengths of red and blue light through a multi-slit diffraction grating, you would see a central peak that is a mix of blue and red light, and then peaks on either side of the central peak that are distinct peaks of either red or blue light. If you expand this idea and shine white light through a diffraction grating, the central bright spot will be a bright white spot. But the bright spots on either side of that will now separate into distinct bands by wavelength, forming rainbow bands of color. The image on the bottom of this slide is an actual picture of white light being separated into rainbow bands of color by a diffraction grating. So in summary, when light passes through multiple small slits, a diffraction pattern is created. The multi-slit diffraction grating consists of alternating dark fringes and bright fringes. The intensity is greatest in the center, and the maximum intensity of the off-center peaks is determined by the envelope of a single slit diffraction pattern. More slits result in narrower bright fringes and allow for the separation of non-monochromatic light into distinct colored bands. The distance from the center line of the screen to the nth principal maximum in a multi-slit diffraction pattern is given by d sine theta equals m lambda, where m is any integer. The distance from the center line of the screen to the mth dark fringe in a multi-slit diffraction pattern is given by d sine theta equals the absolute value of m minus 1/2 times lambda, where m again equals plus or minus 1 or plus or minus 2, etc.